circuitously to where we are today with this. Yeah.
Okay, we'll move on then to Yutaka Hirai on numerical models of the R process, and I'll give you a 3-minute warning.
Oh, thank you. Oh, yes. Oh. Yeah, I think, okay, yeah. Yeah, all right. Thank you very much. And first of all, yeah, I'm very pleased to see you, George, for the first time. And I'm Yutaka Hirai, a JSPS fellow at the University of Notre Dame. So today, I'm going to talk about how the R process enhanced stars that Ian just introduced are formed in the context of galaxy formation. Oops, it doesn't work.
Yeah.
Oh, yeah, good. So the focus of this talk is chemical peculiar stars, well, especially for the R process enhanced stars. As you know, the chemical peculiar stars is very important to understand stellar evolution, nucleosynthesis, and galaxy formation. As George and other many audiences have long-term efforts to understand this. Well, especially for the heaviest element, europium, and the R process elements, we know that there is star-to-star variations on their abundances. For example, the recent observations of the R process R ions have shown that there's, the large amount of the europium abundance in the sample. And, we now classify the R process enhanced stars by R2, R1, and non-RB stars. So, but the importance is that how to extract the fossil records preserved in these stars. So to understand this, we need a proper modeling of this galaxy. So previous studies have shown that for the R process in the low metallicity, the dwarf galaxies are ideal environment. For example, this is our simulations of hydrodynamic simulations of dwarf spiral galaxies with the enrichment of the R process elements. The color contour is our simulated results. As you can see, there are a large number of stars at low metallicity in dwarf galaxies, even if we assume the neutron star mergers as a major site of the R process elements. We show that the slow chemical evolution of dwarf galaxies make it possible to produce R process elements at low metallicity. The right-hand figure shows the kinematics of R process enhanced stars in the observations of the Milky Way. That in the R process alliance, this is an energy versus angular momentum diagram, and the color plots are the sum of the groups of the R process enhanced stars. As you can see, these are clearly grouped in this diagram and shows that possibly they come from the accreted dwarf galaxy now destroyed in the Milky Way. So, however, we have piece of information, but we do not know certain how, when, and how, and where the R process enhanced stars are formed. So the purpose of this study is to understand when and where and how the R process enhanced stars are formed in the context of galaxy formation. So to do this, we have performed a series of very high resolution cosmological zoom-in simulations of the Milky Way-like galaxy. So to perform these simulations, we have developed the original code, Ashura, which is n-body plus smooth particle hydrodynamic simulation code, including some models such as cooling, heating, star formation, supernova feedback, and metal diffusion to compute the galaxy formation. We also compute the chemical evolution simultaneously in simulations by using the chemical evolution library, assuming that core-corpus supernovae, type 1a supernovae, neutron star mergers, and AGP stars. In particular, for the R process elements, we assume that the neutron star mergers exclusively produce the europium. So by using this code, we perform the cosmological zoom-in simulations, which is very high resolution. So we perform the cosmological simulations with a box size of 36 megaparsec, and we pick up the Milky Way-like galaxies like this. So this is the dark matter distribution of our simulations, and this is the stars and gas simulation of our simulated results. The mass resolution of our simulation is the gas mass is about 10 to 4 solar mass, so it has enough resolution to resolve the building blocks of the Milky Way. So to use these simulations, we have computed the enrichment of the R process elements. So let me show results. So this is the simulated europium over iron versus Fe by H in our simulation. From the purple to orange, the yellow is simulated results, and orange is the color and RPA data. And as you can see, the simulation shows that the star-to-star variations in the European mobile ion ratio at the low metallicity. And the right figure compares the distribution of European mobile ion ratio between the observations and the simulations. The observations are with orange and the simulated is overplotted with the blue. As you can see, our simulations have a similar distribution with a European mobile ion ratio, assuming that the neutron star mergers are meta site of the R process elements. So by using these simulations, we have analyzed when, where, how the R process enhancers are formed. The first question is when these stars are formed. So this is the answer. So we have found that over 90% of the R process enhanced stars are formed within 4 billion years from the beginning of the Big Bang, the universe. So this figure shows this. The vertical axis is FAY and horizontal axis formation time, and the color is all stars in the simulations. And well, the red plots are the simulated R process enhanced stars. As you can see, most of the stars are formed in the very early stages of galaxy formation. The next question is where the R process enhancers are formed. We found that over 90% of R process enhanced stars with FAY-2 are formed in dwarf galaxies accreted to the Milky Way. This figure shows the fractions of stars that are formed in accreted components as a function of metallicity. As you can see, the accreted fractions of stars increase toward the lower metallicity. The blue are the R process enhanced stars. The others are not R process enhanced stars. Well, the next question, how the R process enhanced stars are formed. So we have analyzed the gas phase abundance of the progenitors of the Milky Way. So we picked up the progenitors of Milky Way and found that R process enhanced stars with less than FAY -2.5 are formed in low mass dwarf galaxies, which is a typical stellar mass of 10 to 5 solar mass, largely enhanced in R process elements. This figure shows the average gas phase European mobile ion ratio of each building blocks. And this is a 2 example of this, small dwarf galaxies. And as you can see, if the first neutron star merger occurs inside the galaxy, that European mobile ion ratio pushes up. And then it gradually decreases by the dilution of metals. The arrow shows the first R process enhancers form the time. So as you can see, that at the time of the first R process enhancer starts formed, that European mobile ion ratio is still very enhanced. So in such an environment, the R process enhancers are very easy to form. In the case of higher metallicity R process enhanced stars, that is formed by more massive dwarf galaxies. But this case is a locally enhanced gas clump produced by the neutron star. Okay. So this is because that these galaxies have a large gas mass, so they do not have enough time, well, one neutron star merger is not enough to produce the R process elements enhanced in the large building blocks. So in this case, that the high metallicity R process enhanced stars are formed in the locally enhanced gas in the galaxy. So here's the conclusions. So we have performed high resolution cosmological zoom-in simulations of the Milky Way-like galaxies, and over 90% of the R process enhanced stars formed within 4 billion years from the Big Bang in dwarf galaxies accreted to the Milky Way later time. And R process enhanced stars with a low metallicity are formed in low mass dwarf galaxies enhanced in the R process elements. Well, the R process enhanced stars, the higher metallicity formed the more massive dwarf galaxies, but not enhanced entirely. So this is, well, actually my paper is already submitted to the archive, yesterday archive. So if you have interested in, please have a look at it. And also we are now performing the high resolution Milky Way formation and more higher resolution star cluster and dwarf galaxy simulation. So, well, this is applicable for many of your studies. So please let me know if you have any good data to compare and, request to me for the simulations. So thank you very much for your listening.
Questions? Mario.
I just want to understand intuitively what's going on here. So in a larger thing that's already accreted and become a big system, is it because whatever events create the R process material is just diluted more rapidly? Is that what's happening? And then so that the subsequent formation just has our process material, but it not a lot of it compared to, and then conversely in the dwarfs, that dilution takes much longer.
Yes. Yes, because in the case of very small dwarf galaxies, one event has enhanced the RPS elements entirely because gas mass is limited. So the dilution is more difficult to the other places. So that can retain about 100 million years for the RPS enhancement. But in the case of larger system, locally the RPS enhancement, but it's quickly spread out. Yes.
How did you normalize the contribution of neutron star in spirals in this model?
Yes, that is, this case, that that the neutron star spiral rate is very uncertain. That is, normalized by the average amount of the European iron ratio to reproduce the average value and then adjust the yields and the rate.
Had you not included neutron star, would you have still been able to reproduce?
Yes, so that we confirm that we adjust the rates and yields of neutron star mergers, and then the yields and rates are comparable to the observed estimations of GW, the gravitational wave events. Oh yeah, so that what I do is that we fix the average value of European mobile iron ratio to reproduce this the average value of the observations by neutron star mergers. Yes, the amount, and we confirm that the amount they produce is consistent with the observed estimations.
Mike.
The people looking at the R Process Alliance presumably have looked for companion stars on similar orbits to the R Process Alliance stars that would come from the host dwarf galaxy, or has this been done? In other words, you look in the Gaia database and you try to find stars that have orbits similar to the RPA stars, and then associate them with a dwarf galaxy. Has this been done yet?
Yeah, that's what actually want to do, because from the observations we can do only by the speculate that they could come from those galaxies, but all information that we have that's such kind of clustering, it's really or not, it's not well understand. So now we are comparing the simulations and then identify which would really come from the dwarf galaxies or not.
Short answer, Mike. Yes, that can be done. It's being done. And mathematical clustering, independent of chemistry, the stars that share common dynamical parameters in that energy space, those get targeted whenever we get time. So yes, that's being done.
Yeah.
Other question in the room or online? If not, let's thank you again.
Thank you very much.